Okay, let's get started. Mahan, you have my sound? You have my voice? Can you hear me? Oops, seems maybe you can't. Okay, perfect. All right. So last time we talked about representation theory of the Lie group SU2 or the Lie algebra SU2. So, and the main thing we proved was that for any so this is like finite dimensional representations, but really every representation is a direct sum of finite dimensional modules. That's a separate story, but let's look at irreducible finite dimensional modules of the group SU2, the Lie group SU2 or the Lie algebra SU2. We know that in principle, these two things are the same by the relation between Lie group homomorphisms and Lie algebra homomorphisms. And the main thing we proved was that for any dimension D, there is a unique irreducible, up to isomorphism, there's a unique irreducible representation of dimension D, and it can be realized on the space of homogeneous polynomials of degree D minus 1 on two variables. Okay, so that was one important thing we proved. And in the end of the lecture, I wanted to talk about nonlinear groups of it. Are there any questions about representation theory or? Okay. All right, so let's now talk about an example of a group that should be called a Lie group, but it's not a matrix Lie group. And this is really the purpose of the purpose of this course, is to study Lie groups in general, not just matrix Lie groups, although matrix Lie groups form a sufficiently large class to exhibit all the phenomena. But it's important to see at least one example of a Lie group which is not matrix Lie group. So let's consider the Heisenberg group, which we've talked before about. So this is the group of matrices of the form 1A, B, 0, 1, C, 0, 0, 1, with the parameters A, B, and C being in R. Okay, so this is a matrix Lie group because it's a closed subgroup of GL3C. Okay. And oops. And now we would like to consider a quotient of this group by a subgroup N, which is really a discrete subgroup. It's the set of matrices of the form 1, 1, 1, 0, 0, 0, 0, n, 0, where n belongs to Z. So as an abstract group, this is really isomorphic to Z. Okay. And if you think about it, so this group really, because it's like a 3-parameter sort of manifold, at least topologically, this is the same as R3. Okay. It's not R3 as a group. There R3 is a vector space because H is not abelian, but anyway, it's like R3. Okay. And when you take this quotient, what is going to happen? Really, this quotient, it's factoring by a subgroup Z of the third factor, which basically lies here. This is the center. There's like a top left, like top right corner. Matrices of this form, where the parameter n is any real number, it will form the center of this group H. Okay. And this n is contained in the center of H. Okay. And the center is isomorphic to R. So really, you're factoring this group by some central subgroup. And when you factor R by Z, which is like the center module of the subgroup N, you really see S1. This is what I explained last time, right? So what you see is, how do you see that you actually have S1? Because, well, this is like, you take integers and then you identify points that differ by integers. But that basically kind of means like you're wrapping this around a circle, right? So you're wrapping this around like a circle. This is a straight line, and therefore this quotient is isomorphic to the circle with respect to the, so this is really the subgroup of GL1C, which is the set of elements of the form e to the I theta. When you multiply e to the I theta by e to the I eta, you get e to the I eta plus theta. Okay, so you see, this reflects the addition of real numbers as well. Okay. All right. So now, this means when you consider H mod n, really this quotient happens in one factor. So this is like, so at least topologically, so somehow topologically, H mod n is isomorphic to R cross S1. Okay? So you could say that this is like a cylinder cross the real line, because R cross S1, if you take a cylinder and you take the Cartesian product of, I'm sorry, take a circle and take the Cartesian product with a straight line, you basically see a cylinder, right? So this is a cylinder, and this is a like a cylinder Cartesian product of real line. Okay, so it's really like a very nice manifold. Okay, it's a very nice space, and it's also a group, which means like being like a nice space. This means that for any like point on this group, you have a neighborhood that's isomorphic to R3, homeomorphic to R3. Okay, so maybe I should say this is locally homeomorphic to R3. Okay, so this is really a manifold of the group structure. The group structure is very nice. Like the multiplication is a smooth map from H mod n across H mod n to H mod n. But the claim is this theorem, this little theorem that in fact H mod n is not a matrix Lie group. There's no way to realize it as a matrix Lie group. You could say it the following way. So let pi from H to GLV be a Lie group homomorphism. So if well, if n is contained in the kernel of pi, then z is contained in the kernel of pi. So there is no way that the kernel of pi can be n. Okay? So this is the corollary. The immediate corollary is that so G does not have G equals H mod n, or maybe I just say H mod n. Have a faithful representation on a finite dimensional complex vector space. Hence, H mod n is not a matrix Lie group. Okay, so Mahan, you're asking me what is the Lie group structure on the quotient? This is a great question, but we don't need to worry too much about it now because this n is discrete. So so you have this projection map from H to H mod n, okay? Okay. And so then this means that, so you can induce this with a topology, okay? In other words, you can call a subset here open if its inverse image here is open, okay? And you can see so that in fact the open subsets here correspond to n invariant subspaces here, which means open subsets which are unions of some pancakes, meaning like the pancakes being transferred to each other by the action of n. So by the action of elements in the subgroup n, like little n's, the pancakes are mapped to each other in H. Okay, and this allows you to transfer an atlas on H to an atlas on H mod N. Remember, if you wanted a manifold, you needed this atlas, okay? These maps that between Rn and the manifold so that their compositions become smooth. So these maps come from H. The main point is that all of these things will be easy because N is a discrete subgroup. So we have this nice kind of, discrete union of pancakes and so on. Okay. And then we also, now H mod N is also a group because it's just a quotient of a group by a normal subgroup. This N is a central, so normal subgroup. So then we have this product map, okay? And you can see that with this structure, it will be a smooth map. Okay, so inducing the manifold structure on H mod N is really not difficult. I basically explained what it is. I explained what it is by saying that, in fact, H mod N is R cross S1. So it's more technical way of seeing that is what I just said, which is that you induce it as a quotient structure by a discrete subgroup of H. But I also gave a concrete description of it up here. Did I answer your question, Mahan? Okay. Okay, so then if I prove this theorem, then I have the corollary. Does everyone agree? If I prove that any regroup homomorphism which contains N as the kernel will contain Z as the kernel, then it's then I have proved that there is this group which is a manifold and it's a Lie group. It's not a matrix Lie group. Okay. So now, what's the proof of the theorem? The proof of the theorem depends on the following simple but kind of subtle lemma, and the lemma is the following. So let X be in M and C such that it is nilpotent. Which means X to the N is 0 for some N. Okay? And now suppose that E to the X is the identity. Then the claim is that X is 0. So this should be understood as opposed to the following fact that E to the 2 pi I identity is identity. Okay? So it is not true that the exponential map is an injection. So it can map different things to identity, but it cannot map nilpotent things other than 0 to identity. So this guy is just a diagonal matrix with non-zero diagonal entries. It's not a nilpotent matrix. Okay, is it clear? So let's prove this lemma. Oops, if I can make it work. Okay. What's the proof of this lemma? The proof is really easy. So what is E to the X? So E to the X is just 1 plus X squared over 2 plus da da da. And you can factor X from all terms except for the first term. So you can write it as 1 plus X times 1 plus X over 2. X over 2 plus da da da. What you have is still a convergent series because the denominators are n factorials. Okay, so it will converge absolutely. So you obtain 1 plus xp for some p, which is of the form 1 plus x times something. Okay, so now the point is that what you have here is again some expression in x, so it commutes with x, and so this guy is nilpotent. All right. So in other words, maybe I should write it as did I write it correctly? Yeah. Okay. Yeah. So this is what I want to say. So it's P is 1 plus XQ, where Q and X commute. So, and this means that xq to the power n is just x to the n, q to the power n. So it is 0. All right. But then if you look at this 1 plus xq, so this xq is now a nilpotent matrix. Now my claim is that in fact this matrix 1 plus xq is invertible. you can see it in two different ways. So here's the claim. So then maybe I just write the claim. So claim. So this p equals 1 plus x2 is invertible. So this is the claim. Okay. Can you give an argument for this? Why should it be invertible? So I know this xq, this part is nilpotent. So why is this a1 plus xq nilpotent, invertible? Should be a simple trick, yeah?
Difference squares. Keep it, like if you do that enough times, you'll keep the one on the left, but the.
Okay, so how do you want me to write it?
I'm sure. I guess like 1 plus xq times 1 minus xq.
Okay, it's getting closer. Okay. So yeah, so the point, I mean, well, you could try. Okay, so maybe playing with it will lead to the right solution. So the point is that so you want the inverse of this matrix, okay? Well, like for a moment you can think about this as the following, although it doesn't really make sense as matrices, but at least you can try to expand this using the geometric series. So this is like 1 minus xq plus xq squared minus xq cubed, plus and minus, okay? And now the right-hand side, this is actually a finite sum because xq to the power n is 0, right? And that finite sum is indeed the inverse of 1 plus xq. You can see when you multiply, when you multiply the 1 plus xq by the series, you get this telescopic sum. You get some xq to the power n minus xq to the power n's that cancel out. And because the tail of the series is all zeros, this process is valid. Okay, you don't run into any convergence issue or anything. Okay, so then the inverse of 1 plus x cubed, it can be written as a sum, like it's a finite sum. It's a finite sum, but you write it as an infinite sum because there's like all but finitely many terms are 0. Okay, so that's the inverse. So this is a matrix trick. Okay. Okay, so now we know that this guy is invertible. So now how do we use this here? So now when we come back to here, we know e to the x is supposed to be 1. But it's 1 plus x times some invertible guy. Okay, so this means that x times that invertible guy should be 0, so x should be 0. All right, so now if e to the x is 1, then we have 1 equals e to the x, which is 1 plus xp, and so xp should be 0, and this means that x should be 0 because p is invertible. Okay, it was simple. Not so difficult. All is good? Everybody following? Okay. Any questions? Yeah.
Have the x commutes with q, but not with p, or maybe it does, but like.
X also commutes with p, but I just wanted to, point out that this xq is also nilpotent. If you multiply a nilpotent matrix by a general matrix, you might not get a nilpotent matrix. But if you multiply by something that commutes with it, you do. Because in order to show that xq is nilpotent, I need this calculation, which uses the fact that x and q commute. Okay, x and p also commute, but I mean, doesn't. I mean, I didn't use it. Yeah. All right, all is good. Okay. All right, so now using this, the proof of the claim for this theorem is easy. So we wanted to show that if you have a homomorphism with n in its kernel, then z is in its kernel. Okay. So now let's come to the proof of the theorem. Okay, so let pi be a map from H to GLV, be a Lie group homomorphism. Such that n is contained in the kernel of pi. Right. Okay. Okay, so now I'd like to consider the following elements. So now set x underline to be 1 0 1 1 0, sorry. Zero one zero 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 one. And y underline. Actually, I don't want the group elements. I want the Lie algebra elements. Sorry about that. So I want x underline to be 0 1 0 0 0 0 0 0 0. And I want y underline to be 0 0 0 0 0 1 0 0 0. And I want z to be 0 0 1 0 0 0 0 0 0. Okay? So now x underline, y underline, and z underline belong to the Lie algebra of H. Because the Lie algebra of H, what is this Lie algebra? It's just a set of all matrices which are strictly upper triangular. Remember, the like H was like the set of matrices which are upper triangular with one on the diagonal. If I differentiate the one parameter subgroups, the entries on the diagonal should become 0 because like it's the derivative of a constant function. Okay. All right. Any questions? This is just an elementary calculation. And then so now here's the claim. So the claim is that pi underline, which is the derivative of pi, z underline is nilpotent. Okay. So the first thing I want to show is that the image of z will be nilpotent. Okay. So why is that so? That's because so how do I show a linear transformation is nilpotent? By Jordan form, we can for Jordan form theory, you can put any linear transformation on a finite dimensional vector space in the form of Jordan blocks. Okay. And that Jordan form is nilpotent precisely when the diagonal entries are all zeros, because then you will get a strictly upper triangular matrix whose powers will be 0. Okay. So this means that a matrix is nilpotent precisely when its only eigenvalue is 0. Okay. So this is equivalent to showing that the only
Anybody would have found a ring?
Yes, the previous class found a golden ring, and the professor who was teaching it was supposed to take it to the lost and found.
Okay, excellent.
I hope that it's there already.
Yes, thank you. Sorry about that.
Okay, so this is equivalent to showing that the only eigenvalue of this is 0. Okay, so suppose now that lambda is some eigenvalue of this. So I mean, V is a complex vector space, so any transformation has some eigenvalue, right? So, but I want to show that the only eigenvalue is 0. Okay, so let lambda be an eigenvalue of pi underline z underline, and let V lambda contained in V be the corresponding eigenspace. So this means that V lambda is the set of V in V such that pi underline Z underline V is lambda V. Okay? So now, the first step is that pi underline X underline V lambda is contained in V lambda, and pi underline Y underline V lambda is also contained in V lambda. And this is really because of the fact that Z is in the center of the Lie algebra of H. So if you check pi underline X underline V, so for V, so okay, maybe I just write V for V. In here, I have to show, in order to show that pi underline of X underline V is contained in V lambda, I should look at the action of pi underline Z here. Okay? So this is equal to pi underline X underline pi underline Z underline V. And the reason is that XZ is 0 because Z is in the center of this Lie algebra. So pi X and pi Z, XZ. Is 0. So pi X, pi Z minus pi Z, pi X is 0. So I can just look at it this way. But now, pi Z V is just lambda V. So what I get is lambda pi X V. Okay, so what we see is that pi xv is a pi z of pi xv is lambda of pi xv. So for pi xv is also in the eigenspace. And the proof for the other guy is the same. Okay, so everybody happy so far? So I just showed that this z should act nilpotently. Okay, it should be by like the pi of z should be pi of the underline should be nilpotent transformation. All right, I shouldn't change this scaling because this will then does not look right when I create a PDF file. Okay, see, hope that the boundaries are okay. Okay. So now that we know that pi of z is nilpotent, we use another trick, which is really kind of coming from classical quantum mechanics. And that is that this pi of z is pi of x, pi of y minus pi of y, pi of x. Okay. So it's equal to see that z is a bracket of x and y. So this is like pi x, pi y minus pi y, pi x. Now, we just verified that these two guys, they restrict to linear transformations on this V lambda. Okay? Therefore, pi of z as a transformation on V lambda can be written as a commutator. Okay? So this means that the trace of pi of z on V lambda equals the trace of this commutator. But what is the trace of a commutator? Trace of AB minus BA. It's 0. It's trace of AB minus trace of BA, so it's 0. But on the other hand, on the left-hand side, what do I have? I have the trace of this operator, which acts by lambda on this space V lambda. So the trace is actually lambda times dimension of V lambda. And V lambda was a non-zero eigenspace, so the dimension of V lambda is non-zero, but lambda times that dimension is 0. Hence, lambda should be 0. Okay. Now, I said that this comes from classical quantum mechanics, so does anybody know why? So this commutator relation xy minus yx, it is somehow standard, and again, this sort of the most basic example of a quantum model is called the quantum harmonic oscillator, the simplest kind of Schrodinger equation that you can write and solve. And you could in that setting, x and y are replaced by two operators that represent the position of a particle and the momentum. And this pi x pi y minus pi y pi x there equals the Planck constant times I. And that is really the statement of Heisenberg uncertainty principle. But the reason that that can happen over there is that those two operators are now on infinite dimensional vector spaces. So you cannot use this trace condition to say that that's a contradiction. So you can have pi x and pi y on infinite dimensional space where the commutator is non-zero. In fact, in that setting, it turns out to be the Planck constant. And you can actually prove a version of Heisenberg uncertainty principle, which I suppose most of you have heard about. The Heisenberg uncertainty principle, you've heard about it? Okay, does anybody know what it is conceptually? No? Nobody knows what it is? Do you know what it is?
Can't know like the momentum and position of particle at the same time.
That's right. The particle does not have a very precise momentum and a very precise position at the same time. If you measure the position, then there will be uncertainty about what the momentum is. There will be just a probability distribution. And if you measure the other one, the momentum, there will be no certain position. So these two things cannot be, you cannot identify, unlike Newtonian mechanics where a particle, a moving object has like precise position and velocity and, momentum and, so on, and like energy level, everything is precise. In the quantum setting, you can't have all of them at the same time. And you can interpret that as basically your level of precision cannot go beyond this Planck constant in some sense. And that's related to this commutator relation, okay? But in finite dimensions, that can't happen. So as we saw, all right, and we use this in some proof, which is not really quantum proof, but anyway. Okay, so now what's the conclusion? We just proved that this operator pi is nilpotent, but we're not done yet, okay? So now the next thing is that so now you can look at right. So now you need to look at the exponential map. So you should look at, so now the next step is like, so next we consider pi of e to the z underline, okay? So here, I should tell you what the exponential map here is, but the exponential map, remember that I identified this group as a, like topologically with R cross S1. So I would like to take the exponential map on R mod Z, I should really take like theta goes to e to the 2 pi I theta, right? Because I want the integers to be mapped to the same point. I want, like a 0, 1, -1, so on, to be all mapped to the identity element. The exponential map should wrap around the real line around the circle, okay? All right? And so this means that if I look at the exponential of this e to the z, then, what is z? Z has a 1 on that corner. It's 0, 0, 1, 0, 0, 0, 0, 0. And if I do the exponential, basically I get this e to the power 2 pi I here. So I really get a 1 there. So the exponential of this one will be 1, 0, 1, 0, 1, 0, 0, 0, 1. Okay? And what do I know about pi of this one? Well, this guy is in N. Therefore, I know that this is identity. Okay? But on the other hand, pi of e to the z underline, by the standard properties of Lie group homomorphisms and the related Lie algebra homomorphisms, this is just e to the pi underline of z underline, which happens to be I, okay? And what I know from what I just showed is that pi underline z underline is nilpotent. And hence by the lemma, pi underline z underline should be 0. All right. And this basically completes the proof, because this now means that pi underline of t times z underline is 0 for all t. And finally, pi of e to the t z underline is e to the t pi underline z, which by what I saw above, it's just e to the 0, which is the identity. So the whole one parameter subgroup is mapped to the identity. But what is this? This is just the set of all matrices. Maybe I just write as the set of matrices of the form e to the t z underline for t in R. It is just the set of matrices of the form 1, 1, 1, 0, S 0 for S in R, which is the set which we call the Z. I guess that's what I use, right? A little bit of unpleasant notation maybe, but yeah. Yeah, the center. All right. So the center happens, the center is just these matrices of the form 1, 0, S, 0, 1, 0. I mean, matrices which are like 1 on the diagonal and they have just S in the corner, but that S can be any real number. Okay, so this proves the theorem. This completes the proof of the theorem. That the kernel cannot be just N. If it contains N, then it will contain Z. Okay? Everybody happy? All is good? Okay. Okay, so now we know that in fact non-linear Lie groups exist. Not every Lie group is a matrix Lie group, and well, we should always develop a theory with an eye towards including those groups because they're also very important. Many interesting Lie groups are not matrix Lie groups. Okay, but let us also try to proceed in a slightly different direction and try to answer some fundamental questions. So here is like, now I want to shift gears slightly from this topic and talk about the following important natural questions that one can ask, and we would like to try to answer them. So one can ask the following 3 natural questions. So question 1. We have seen that starting from a Lie group, we can construct a Lie algebra, the Lie algebra of that Lie group, and up to isomorphism, it is unique. So it's a characteristic of that Lie group. So now the question is, can we go backwards? So given a Lie algebra G, the question is, does there exist maybe a matrix Lie group, maybe I mean just a Lie group, G such that the Lie algebra of G is isomorphic to G? So here's the first question. Given a Lie algebra, can you always construct a Lie group with that Lie algebra? Okay. The second question is, if you have a homomorphism between Lie algebras of 2 Lie groups, does it always ascend to a Lie group homomorphism? So suppose G and H are matrix Lie groups. And phi from Lie G to Lie H is given. The question is that there exists. Does there exist a Lie group homomorphism. A capital phi, such that when you compute the derived homomorphism, the underlined one, you actually get this phi. Okay, so again, it's like going in the opposite direction of what we did before. Starting from a Lie group homomorphism, we constructed a Lie algebra homomorphism, this underlined phi. The question is, if you have something below, can you go up? And the third question is the following. Suppose you have a Lie algebra and you have a subalgebra of that Lie algebra. Does that subalgebra, suppose that the Lie algebra, the big Lie algebra is the Lie algebra of some Lie group G. Does that subalgebra correspond to a subgroup, like a closed subgroup of G? All right, so G, let's say G is a matrix Lie group. And H, a Lie subalgebra of the Lie algebra of G, which means a subspace, which is a Lie algebra with the induced bracket from the Lie algebra of G. So the question is, does there exist, or rather, maybe the question is, does there exist a closed subgroup such that the Lie algebra of that subgroup is this subalgebra? Okay, so there are three natural questions. Okay, so there are a whole bunch of questions in the chat. Oh, I've already looked at all of them, it seems. Okay, all right. Okay, all is good. So the goal is to answer these questions. All right. So this is really the purpose of the rest of the course. And the answer to the first question is a fundamental theorem of Lie. Okay. In fact, also the third question is a fundamental theorem of Lie. And all of these questions are related to a sort of a basic question we asked earlier in the course. What is the relation between the exponential of e to the x plus y and e to the x and e to the y? How can we express e to the x plus y for two matrices x and y? Okay. Now, here is a naive strategy for question 2. So maybe it's just a naive strategy for question 2. So remember this. What is the relation between this capital phi and its derived map? So like capital phi of e to the x should be e to the lowercase phi of the Lie algebra element, right? So why can't we try to define this capital phi this way? Okay. So here's the naive strategy. Given phi going from G to H, we can attempt to define capital phi by capital phi of e to the x equals e to the little phi x for x in the Lie algebra. So what is wrong with this? Maybe we solved question 2. Maybe I lied to you that this is not easy. What's the problem with this? Why can't I define this capital phi? Then underline phi would be little phi. Yeah?
Exponential map may not be surjective.
Yeah, the exponential map might not be surjective. It might not also be injective, right? So there will be ambiguity about this map, right? It might not be defined everywhere, and it might not actually be a consistent definition, all right? But at least we know that the exponential map is a bijection near the identity element, right? A neighborhood of 0 is mapped bijectively to a neighborhood of identity. So such a definition would work near 0. At least locally, such a definition would make sense, right? All right. But still, even if that makes sense, we have another problem. So, well, okay, maybe this makes sense locally, maybe. So this makes sense, at least locally. So, but then we need to know that, in fact, we got a group homomorphism. We need to know that phi e to the x, e to the y equal to phi e to the x, phi e to the y. Okay? So this will be another problem, right? Now, in order to tackle this second problem, we can use the following trick. And this is just a trick for the moment. It's not a precise solution. It's not a theorem yet, but this sort of shows you what we want to do. All right. So the idea, maybe I should say idea or / claim. So I would like to define like phi of e to the x, e to the y. So now, well, this is e to the something, okay? Hopefully, it's like if you're in some small neighborhood of identity, you can expect that this e to the x, e to the y is e to the something, okay? So what is that something? How can we express that guy in terms of x and y? This is really the claim. So if I want to find that guy, I can take the log of e to the x, e to the y, and then I can ask what it is as an element of the Lie algebra. So what we're going to find is a formula of the following form. X plus y plus 1/2 the bracket xy plus 1/12 xy plus a whole bunch of other terms. And I cannot write an easy formula for this. I mean, there is a formula, but I mean, there's like lots of factorials involved. So yeah, Mohan, I guess we basically talked about the same thing. You said it's not defined globally, which I think you're correct. And now I'm just explaining what that means, okay? Like, or rather how to sort of get around this issue. All right, thanks for your comment. All right, so now let's look at this log of e to the x, e to the y. This is the claim. The claim is that you can actually write this log in this form, okay? So what this means is that if we have this, then we can check this relation in the following way, the multiplicative relation in the following way. So we have this capital phi of e to the x, e to the y. So from this, we see that this is capital phi of e to the log e to the x, e to the y. Okay, so far I didn't do anything, just made things more complicated. But I can write this as capital phi. I'm sorry, this is like phi, or rather e to the little phi of log e to the x, e to the y, which means this is e to the phi of that series, x plus y plus 1/2 xy plus 1/12 xy plus blah, blah. And if I'm lucky, that series is absolutely convergent for x and y sufficiently small, and therefore I can let this phi pass through. So I can just write this as phi of e to the phi x plus phi y plus 1/2 phi x phi y plus da da da, all these terms. And now again, by reversing the process, I know that this is e to the log of e to the phi x, e to the phi y. So then this is just e to the phi x, e to the phi y, which is capital phi x, capital phi e to the x. Okay. So if I had some power series expansion for this log of e to the x e to the y, then I could use it to define a local group homomorphism, not a group homomorphism that's defined globally, but at least on some open neighborhood of the identity element, it's defined and preserves product as long as the things involved in the product are in this neighborhood. Okay, so at least locally I have group homomorphism. Okay, near this point, it has not been defined yet globally, but at least locally I can solve this problem. I can get around this problem. Okay. So this is really the goal. So the goal is really to find this formula, to prove that such a formula exists. Okay. How many of you are familiar with such a formula? Nobody had seen this before? No? Okay. All right. So this formula, it bears the name of 4 different mathematicians. Well, sometimes 3, sometimes 4. Baker, Campbell, Hausdorff, you've heard, and Dinkin. So if you look at some textbook written by a Russian, they also include Dinkin. So, and Dinkin is a famous person in lead theory, but also in probability theory. But anyway, that's a different story. So 4 different mathematicians would like their name on this theorem. So this means it's an important result. The proof is also not easy. And the goal from now on to basically give an idea of how this is proved with as much detail as possible within the scope of the course. Okay. All right. So the next thing I want to do is I want to show you how this process works, say in the case of the Heisenberg group, where the Lie algebra is 2-step nilpotent, and therefore this series will not be infinite. In general, you could have a power series, but well, if you know that the commutators vanish after some point, then you actually have a finite sum. Okay, so this is the next goal, to show that this technique, this idea works, at least say in the case of the Heisenberg group. And this will be sort of a prototype for the general case. All right. All right. So here is the claim. So here's the first statement. So suppose that X and Y are n by n matrices such that XY, the bracket of X and Y, which means XY minus YX, commutes with X and Y. Okay, so this commutator is the usual bracket on matrices, XY minus YX. Okay. So then e to the x, e to the y can be written as e to the x plus y plus 1/2 xy. So as you see, this is a special case of that formula, right? X, y, and the bracket of xy, they actually form a Lie algebra. Okay. And in fact, an example of such xy would be the elements that generate the Lie algebra of the Heisenberg group, the Heisenberg Lie algebra, which you just saw like a few minutes ago. Okay, the x underline and y underline would be examples of this. Okay, all is good. All right. So let me see. There's a question in the chat. Okay, so the question from Mahan is that, well, so we define a local group homomorphism this way, if we can, develop all this log technique and so on, this BCH formula. But what about going from the local homomorphism to a global homomorphism? Will we resolve this issue? Yes, I will explain how this can be resolved. This is basically part of like the fundamental theorems of Lie. So by the end of the course, I will explain how to do this. Yes, Mahan. So we will get there, but that requires other tools and techniques. Well, I mean, by the end of this part of the course, because the last few lectures of the course are slightly different topics, but I guess by early November, I mean, by mid-November, you will know this, let's say. All right. Okay, so now how do we prove this? All right. So the proof so there are various ways to do this, but the proof technique is also somehow of analytic nature to somehow give you an idea of the proof technique for the general case. All right. So here's the technique. So the technique is actually first we prove something is slightly more general. Okay. I mean, not really more general. Maybe it looks more general, but it's really equivalent. So we prove more generally that e to the tx, e to the ty equals e to the tx plus ty plus t squared over 2xy for all t in R. Okay? So really, if I replace like x by tx and y by ty, I just get this. So in other words, this is really an equivalent statement. You would say, oh, you just introduce a redundant parameter. But sometimes a redundant parameter can come to rescue. How can it come to rescue? Because now I have one parameter subgroups and I can differentiate. Okay, remember a lot of like techniques, like a lot of these theorems we proved using differentiation, and then the evaluation at identity or at zeros. Okay. So I introduced this extra parameter to be able to differentiate something. So what do I want to differentiate? Well, I want to differentiate both sides of this. At t equal to 0, I have equality, obviously, because it's e to the 0 equals e to the 0. And now I want to differentiate both sides. They are equal at 0. The derivatives, I want to say that they are the same, so they should be the same function of t. And so for t equal to 1, it gives the formula I wanted. Okay. I'm going to do this, but it's slightly more subtle. Maybe it would be that I know that they have the same initial value at t equal to 0, and the two sides satisfy the same differential equation. Now I can use this ODE theorem, which I shouldn't have assumed that you know, that any ODE with a given initial value will have a unique solution. Okay, at most one solution. And therefore, the two solutions should be the same. One with the left-hand side, the other would be the right-hand side. Okay? All right? All is good? All right? So let's try to do this. So I set AT to be the left-hand side, which is e to the tx, e to the ty, and BT to be the right-hand side, which is this more complicated thing, e to the tx plus ty plus t squared over 2xy. How much time do we have? Okay, we have, okay, about 15 minutes. All right. All right, so now first let's differentiate the left-hand side, the d over dt of AT. So it's a product of two matrices depending on t. So I can use the Leibniz rule. I should differentiate e to the tx at t. So I get this I differentiate at t, so I get tx times e to the tx, e to the ty, plus ty, e to the tx, e to the ty. Actually, I don't get the e to the ty because x and y don't commute. I have to do this carefully. Oh, wait, x and y. Okay, so let's see. Okay. Okay, what do I get when I differentiate? Let me just do this more carefully for the first one. So I get tx e to the tx e to the ty plus e to the tx y e to the ty. Okay, but I think I can do a trick here. I mean, there's a t also here. I shouldn't forget the t. Okay, let me check. Okay, so okay, let's keep it as is at the moment. So, but I don't like the way I got it. So I should have. All right, so let me see. Okay, I will try to explain what happens. So I really want to move the ty past the tx, and I get this tx. Actually, so okay. All right. First of all, I'm doing a derivation like mistakenly. So I don't have a t. I should take the derivative of tx. That's just x. Okay, you guys should tell me how to differentiate. All right. So the derivative of e to the tx, I should differentiate the argument. I'm using the chain rule. So I should get the derivative of tx, which is x, multiplied by the derivative of the exponential. But the derivative of exponential is like is just itself. Okay. So I really get x e to the tx e to the ty plus e to the tx, either y e to the ty, but I could just, or maybe I should just keep the y in here, okay. Y e to the ty. So I need to explain why I can move the y past. So I want to write it as e to the x plus y, e to the tx plus e to the tx e to the ty, which is basically x plus y at. Okay, so this might actually come up in the calculations that come next. Now I don't remember this, but let's just keep this and I'll explain this. Okay, if I didn't find it, I'll explain in the notes. All right, so now the next thing I want to differentiate, this right hand side thing. So I want to differentiate d over dt of bt. So that is the derivative at any t of e to the tx plus ty plus t squared over 2xy. Okay, so again, it's the same technique. Okay, now I realize why I didn't get the right thing. I just rushed through my notes. Okay, so let me correct it. So this is not the AT and BT that I want to take. Okay. All right, so I mean, I want to take another thing. Okay. I would like to take the following. Okay, yeah. Okay, so we want to rewrite this. Okay. I missed this important step. Okay, so to rewrite this as e to the tx, e to the ty, e to the minus 1/2 t squared xy equals e to the tx plus ty. Okay, now this is much better. How do I do this? Okay, so now I basically multiply both sides by this quadratic t squared term. Okay, so let me correct all of this. All right. Okay, so multiply on the right. So maybe I should say multiply on the right by e to the minus 1/2 t squared xy. Okay, so now here we use this property, this assumption. So if I multiply on the right by this e to the minus 1/2 e to the e to the minus 1/2 t squared xy, okay, so on this side I just get the left hand side here. Okay, nothing happens. But on the other side, the point is that this matrix commutes with these two guys. Okay, and when I multiply, then I can cancel this. In other words, I can think about it as the following form. I can think about it as, so the right hand side is e to the a, e to the b, e to the minus b, where a is tx plus ty, and b is 1/2 t squared xy. And I know that x with xy commutes and y with xy commutes. So I know that AB equals BA. So then I can write this e to the A, e to the B, e to the A, is it plus B? E to the A plus B, sorry. This is e to the A plus B. So e to the A plus B. E to the minus B. I can now write it as e to the A. Okay, so this is because A and B commute. I mean, really, that's because this you can write as e to the A, e to the B. Maybe I should just write this right here. Okay. Okay. So now it looks simpler on the right hand side. Okay. And now I will continue with this derivation technique. Okay. So is it clear what I did? So I mean, in the previous calculation, I forgot to do this. So I get a product of 3 terms on one side and just one thing, e to the something on the right hand side. If I did it the way I was doing it, I would not get this x plus y nice thing. Okay. All right. So now I should redefine my A and B. So maybe I should also mention that this term also appears here. Okay. All right. So now I call the left hand side A and I call the right hand side B. All right. So now set AT to be, what's the left hand side, which is e to the tx, e to the ty, e to the minus 1/2 t squared xy, and B to be e to the tx plus y. So I need to show that these two guys are the same. Okay, and they don't cancel in an obvious way. Okay. Okay, so now let's compute the derivatives. The B is easy, right? So d dt of bt is the derivative of e to the t times x plus y. So I use the chain rule. It's the exponential times the derivative of the inner function, which is like a linear in t. So I get this x plus y. I can put it on either side because x plus y commutes with any term of e to the x plus y. Okay. And now let's do the other one, which is a little bit harder. Time. Okay. We have only 4 minutes. Okay, let's do this quickly. Well, now I have three terms. Now I have to use this Leibniz rule. So the derivative of first, which would be x e to the tx. Maybe I just keep it like this. E to the ty, e to the minus 1/2 t squared xy, plus e to the tx, the derivative of the middle one, which is y e to the ty, e to the minus 1/2 t squared xy. And a third term, which is the derivative of the last term. So you get e to the tx, e to the ty, and then the derivative of this minus 1/2 t squared blah, it's like a minus t. The bracket of xy. E to the minus 1/2 t squared xy. Okay? Now I need to simplify this whole thing, right? But the point is that first, well, I can put this x here. And now this x e to the ty, I can simplify this a little bit. So I can write this as e to the ty, e to the minus y, minus ty, x e to the ty. And now this should remind you of something. This is the exponential of the adjoint, right? So I have this e to the ty, e to the minus t add yx. Okay, this was the relation about like the relation between the adjoint group homomorphism and the adjoint Lie algebra homomorphism. Okay, this we had before. You remember this? I mean, just like e to the add is add. This is this relation. Maybe I just write it here. Okay, add is e to the add. Okay, I mean, I don't know. Maybe I just write as add. Add e to the x is e to the add x. All right. This time, of course, this x is ty. All right. So now, but now I can just write the series here. So I can write this as e to the ty times. Well, then I have to write the series for this e to the minus t add y. So there's the identities, which is acting on x gives me x, minus t times add y of x, which means yx, plus t squared over 2 times yx, and a bunch of other terms. But already I get zeros from here. Any other term will be like y, then x. So, but I know that yx and y commute from our assumption, right? From this assumption. All right, so let's go down there. So, so I end up with e to the ty times x plus t times xy. I mean, negative yx is just xy. Okay. And now I can also write this y e to the minus 1/2 xy t squared. Okay. So this term. So here, so I was able to push this x to here, but this x can still also move past this guy because this x commutes with this bracket of xy. So I can put this x to the far right. Same, I can put this y first past this e to the ty. That's just because y and y commute, and again to the far right. Okay, and the only thing is this last term. I can then, but still I can move the xy past. All right. So then what I get, so move y to the right. Maybe I just write move y to the right. And the same like xy e to the minus 1/2 t squared xy. So again, move the xy to the right. They are possible because of the fact that the argument of the exponential commutes with this matrix that is moving to the right. So as a result, consequently, what is the derivative of AT? What happens to the first term? So to the first term, this x moves all the way to the right. With the exception that when x passes through y, I should write this e to the ty times this guy. But then the x and the other guy will pass to the right. Okay? So I end up with e to the tx, e to the ty, e to the minus 1/2 t squared xy times x plus txy. And then there's so now for this term, the y passes all the way to the right. So I get the y. And for the last term, the minus txy will pass to the right. So I should just write minus t times. And now you see that this guy and this guy cancel. And this is just AT. So what I got is like AT times x plus y. All right. So now what we have is that d dt AT is like AT x plus y, and d dt bt was also the same thing. Okay. And we also know that AT A0 equals B0. And now from the fundamental theorem of ODE, you have two differential equations with the same initial value. I mean, the equations are the same. There are two different solutions of the same equation, but the initial values are the same, so they have to be the same. And now you set t equal to 1, and you get the result that you want. Okay, so now this is basically enough to define the corresponding Lie group homomorphism from a Heisenberg group to another Lie group. So that technique, that trick that I was trying to explain, which would only work locally in general, and it also needed this logarithmic thing, now can be made precise for the Heisenberg Lie group. I can explain this next time. And then we want to generalize this by like proving this BCH formula, giving a statement of proof of this BCH formula. We want to generalize this technique to all Lie groups. So that will be the next goal for the course. Okay, I guess that's it for today. Are there any questions? Okay, if not, then see you everyone on Wednesday.